In this video, we are going to go over section 4.6, optimization. The goal of this section is to solve application problem that involve either maximizing or minimizing value. So it's building on, we have been working on finding maximum or minimum value, but we are going to apply to our application problem. So here's some strategy for solving optimization problem. Number one, introduce the variable. Look for relationship among the variable and construct a mathematical model to form maximize or minimize on the interval I. So we are looking for some function to max or min. Find the critical values that's taking the first derivative, set it equal to 0. Use the procedure developed in section 4.5 to find out absolute maximum or absolute minimum where it occurs, because we are looking for maximizing function, so we want the absolute max or absolute min, not relative max or relative min or local mean, local max. So we are going to quickly reference back to 4.5. And then finally, number 4, use the solution to the mathematical model to answer all the questions asked in the problem. So we have 4 problems to work on this section. We'll begin with number 1. Find 2 numbers whose sum is 50 and whose product is maximum. So first, let's take a look at some variable. Let's introduce the variable. We need 2 numbers. I don't know those 2 numbers. So let's call this X and Y. Okay. What are we maximizing or minimizing? We have 2 things, sum, product. We want to max the product. Product means we are going to multiply. So we are going to maximize our product function. So let's just call it our product function x, y, subject to our sum function, which is x plus y equal to 50. So we want to maximize our product function, not sum function, because it tells you here max the product. All right, so now let's keep going. So since we want to work on with the product, and then I have 2 different functions, I need to use my subject function and then solve for one of the variable and then substitute, so we are dealing with only one variable. So let's solve for x here. So I can subtract y both sides. So x is equal to 50 minus y, and let's plug it in over here. So we are dealing with just one variable. You could do the opposite, no problem. You could start solving for y and substitute that and solve for x, vice versa. Variable does not matter which order. So we have our product function as 50 minus y times y. Okay, now I'm just being a little bit picky. You can leave it as p, or I'm just going to say p of y because our equation now is everything in y. So p of y is equal to 50y minus y squared. There's our function that we want to maximize. Step 2, find the critical point. So that means I need to take the first derivative and then set that equal to 0. So that will be 50 minus 2y. And let's set that equal to 0 to solve for y value. Let me erase this part so we have a space. So to solve y, I can add, I can add 2y, add 2y. 50 is equal to 2y. Y is equal to, I get 25. Now with y25, I can solve for x. So x is equal to 50 minus 25. So x is also 25. Now that is one of the that is our critical value. So let's write out the sentence. So this means 25, 25 is the critical value. Now, going back to section 4.5 to see which one is a absolute max or minimum. Since we are looking for maximum, we'll look at the absolute maximum function. So pulling out 4.5 notes, we found the absolute maximum by having this first derivative of our critical value equal to 0, and then f double prime, second derivative of function at the critical point is a negative. Then we call that absolute maximum. So I'm going to have a quick screenshot. And then let's go back. And then let's add a page. Okay, so this is what we are checking. And then we are going to take the second derivative because we want to check this condition here. This is what we are checking here. In particular, we want to look for this part here. So our first derivative function from the first page was this one here, 50 minus 2y. So our second derivative will be constant is a 0, so negative 2. So since our second derivative is always negative because it's negative 2, we get that 25, 25 was the critical value that gave you 0. And also we have second derivative function, which is negative 2, which is less than 0. So our number 25 and 25 is the two numbers, x and y, which is 25 and 25, have a sum 50. And you can check 25 plus 25 is 50. And this gives maximum product, which is 625. That's it. Okay, the first one is pretty simple and easy. Let's take a look at the second one. Dimension of a rectangle with an area of 16 square feet that has a minimum perimeter. So we have a rectangle. So what do you know about rectangle? Area is given, and then we want to minimize perimeter. So rectangle is, we have x and y, so the area function is x, y, and then we want to minimize perimeter function. There you go, minimize. Let me put it on. Perimeter. How do you find the perimeter? That's adding all the sides, so 2x plus 2y, and then subject to our area function. So let's start filling the blank. So perimeter is 2x plus 2y. Now we are given the area values, so 16 is equal to xy. We are minimizing, so I'm going to be using this one. Substitute either x or y, doesn't matter which one, because this is the function that we want to deal with, minimize. So let's solve for y here, then dividing x I have 16 over x. Let's plug that in into wherever you see y. You can solve for x and substitute that value, doesn't matter. Then you're solving for y first. Here I'm substituting y, so I'm solving for x first. So p is equal to 2x plus 2 times y, which is 16 over x. So I have p is equal to 2x plus 32 over x. So in other words, p is 2x plus 32x to the negative 1. Now, second step tells us that find the critical point, that is, first derivative is equal to 0. We want to find the x value where it's equal to 0. So let's find the first derivative. That will be 2 minus 32x to the negative 2, right? Negative 1 comes down and then subtract by 1. So let's find the critical value. So that means we set the first derivative function equal to 0. So that means I'm going to add 32x to the negative 2, add 32x to the negative 2. I have 2 is equal to 32x squared. I just put it into positive. 2 is same thing as 2 over 1. So we can set up cross multiplication. So I have 2x squared equal to 32. Divided by 2, I get x squared is equal to 16. To have x by itself, I'm going to square root. So x end up being plus or minus 4. Now, because we are talking about length of a rectangle dimension, I'm going to exclude negative value. You cannot have a negative length. So the only appropriate x value is 4. Okay? So that's our x value. Now, let's double check. You can also solve y at this point here. So y will be 16 over 4. So I get y is equal to 4 as well. So that means 4, 4 is our critical value. But we want to double check. You cannot assume that this is maximum or minimum. We need to check. We want to minimize the perimeter. So that means, going back to our 4.5, we are looking at second derivative at 4, 4 has to be positive. We already got this part here. We found that this gives you 0 because that's what we did. We set it equal to 0 and solve. Second condition, we need to check. So let's take a second derivative. First derivative from the previous page was this over here. So p prime was equal to 2 minus 32x to the negative 2. Let's take a derivative for the second time. So that will be the 2 is just 0. Negative 2 with this negative 32 will make it 64x to the negative 3. So we want to check the c value. So that means x is 4. So let's double check. If double prime at 4, the critical value is greater than 0. If it's greater than 0, that is an absolute minimum value. So here 64, x was 4, raise it to negative 3. In other words, 64, 4 cubed, I get equal to 64 over 64, 1, which is greater than 0. So we got the second condition. So indeed, x equal 4, y equal 4. Our critical value is the absolute minimum. And then because we are giving a length, our unit is 16, so it's going to be 4 by 4 dimension. So it's more like a square, not a rectangle. All right? Moving along onto number 3, another area in rectangular problem. This is a slightly different. Okay, so they modify a little bit. So let's take a look and let's pay attention to the question because it gets a little bit tricky. A fence is to be built to enclose a rectangular area of 900 square feet. The fence along 3 sides is to be made of material that costs $14 per foot. The material for the 4th side costs $42 per foot. Find the dimension of the rectangle that will allow for the most economical fence to be built. Now, there are a couple things that we want to pay attention to. They want to know most economical. That means minimize it. Minimize the function. What are we minimizing? The dimension of the rectangle, not the area dimension. That means perimeter. So we want to minimize our perimeter value, perimeter function to subject to our area function because area is given. Okay. Now, second thing is we have kind of like different sides cost different cost. So if you have this rectangular area, a fence is to be enclosed in the so we have a rectangular area and then a fence is to be built to enclose a rectangular area of 900 square feet. Fence along the 3 sides are made. So here we have this part here. So we have, this is what's going on. You have X, X, Y, Y. Now, 3 sides are costing $14 per foot. So this will cost 14, 14, 14, and then material for the 4th side, whatever the 4th side, cost 42. Okay, so that's what's going on here. 3 sides cost $14 per foot, and then the 4th side costs 42. Find the dimension of the rectangle that will allow for the most economical fence to be built. So what is our perimeter for this part? That will be I'll put P here. 14x plus another 14x plus 42y plus 14y. And then our area function xy is given as 900. Okay. All right, let's keep going and take a look. So perimeter is equal to, I end up having 28x plus 42 plus 14 will give me 56y. So since we are maximizing perimeter, I take this one and then solve for x or y, up to you, and then plug it in. Now I want to solve x because eventually in our definition, we are looking for the x value. Okay, so we'll stick with the solving for x. So over here, I can solve x by dividing by y. So 900 y to the negative 1 equals x. And that's what I'm going to replace my x value with. So P is equal to 28 times 900 y to the negative 1 plus 56y. So 28 times 900 will equal to 25200 y to the negative 1 plus 56y. So we found the perimeter function that we want to minimize. To find the minimum value, we'll take the first derivative. So we need to find the critical value. So that is first derivative function. Set it equal to 0. So let's take the first derivative. So that means negative 1 comes down. So I have negative so this is terms of y. Negative 25200 y to the negative 2 plus 56. Let's set that equal to 0. So I'm going to add 25,200 y to the negative 2 on both sides. So I have a 56 is equal to 25200 y squared. Same thing, I'm going to cross multiply. So I have a 56y squared is equal to 25200 divided by 56. And let me make this a little bit smaller. So I'm getting y squared is equal to 450. Okay. Square root to solve y, and this will be equal to 3 root 50, which is approximately 21.21. I'm only taking the positive again because we want to find the length of a rectangle, so negative doesn't make sense. So let's solve for x here. So x is equal to, substituting y as 21.21 to the negative 1. My decimal number, I end up getting 424.43. That's my x value. So that means 424.43 comma 21.21, that's my x and y value, is the critical point. So let's copy this one again. We want to see if this critical point is the minimum, because we want to minimize. So that means we want to take the second derivative, and that value at 424.42, because that's my x value, has to be a positive number in order to be absolute minimum. So let's check. So let's take the double derivative. Here's our first derivative function right over here. So I'm gonna write it out one more time. So our p prime of y was negative 25,200 y to the negative 2 plus 56. And then if I take the double prime, I have negative 2 comes down, so I'm going to have positive 50,400 y to the negative 3, and 56 disappear. Now let's plug it in. Oh, my mistake. This is in terms of y, so I should plug it in this one here. Okay. If you did it other way, the x, then you plug it in 424.43, but I put it y, so we use y value. So p double prime 21.21, 50,400, 21.21, raise it to negative 3. Let's use that with the calculator. I'm getting, raise it to negative 3. I'm getting positive 5.28 rounded to the 2 decimal place, which is greater than 0. So we got the second part also checked. So that means, what does that mean? Our critical value, this one over here, is our minimum value. Absolute minimum. So let's write a final sentence. This means a rectangular field that has a width of 21.21 feet at a cost of $14 per foot, right? This one here. I'm sorry, this one here, width. So in this case, my width will be my x and then this will be my length, or vice versa. It's just a label. And then we have a length of 42.43 feet at a cost of $42 per foot. Will minimize the cost of our fence. Okay. And that value is, which is approximately, so how much does it cost? Well, let's find out. This is our function. So we have 28x was 424.43, and then we have 56y, which is 21.21. So how much? Let's check. 28 times 424.43 plus 56 times 21.21. Hold on, let me just double check. I made a decimal error because I knew something was very large in terms of money. This one is actually 42.43. I put the decimal place in the wrong place. So that makes sense more because that's huge, 42.43. But in terms of our answer, it does not change, 42.43. That makes a lot more sense. So let's fix everything. 42.43. So let's do it one more time. So approximately $2,375.80. Okay. All right. Let's move on to our last problem. Our last problem is actually a homework problem. It's number 11. So let's take a look. A manufacturer of hospital supplies has a uniform annual demand for 180,000 boxes of bandages. It costs $10 to store one box of bandages for 1 year and $250 to set up the plant for production. How many times a year should the company produce boxes of bandages in order to minimize the total storage and setup cost? Okay, so we want to minimize our storage and setup cost. So let's write down a couple things. So for cost function, let's call it C of X, there's two things. Total, so storage fee, which is right over here, $10 to store, so it costs $10 to store, and it also has a setup fee, setup cost. Where's the setup cost? $250 to set up a plant for production. Okay, so that means total cost, I have to consider that storage cost plus setup cost function. Okay, it comprises of two things. Okay, and then we want to minimize this function here. We want to minimize our C of X. Okay, let's also label some unknown X. What is our X going to be? X will be the number of boxes of bandages produced in each production run. Okay, all right. Now, how much does it cost in terms of storage? $10 to store one box, but we are not only storing one box, so it's 10 times of how many it is. So let's say X represent the number of bandage produced in each production run, and then we are just gonna have average number storage in each day, so divided by 2. Okay, because we are not going to only store one box. How many boxes that we produce in each production run, we'll take the average of it each day. Adding setup cost is $250. Same thing, but how many do we have? Well, the number of production run is we are creating this demand. So what we have total of 180,000 divided by X. The number of boxes of bandage produced in each production run. Okay, so that will be our C of X function, where X is between 1 to 180,000. So that will be our function right over here. Okay, so just remember, read it carefully. We have two different costs that makes up the total cost. So C of X will be our total cost. So let's simplify. So this reduce 5X. 250 times 180,000 will be 450, 000, wait, 1, 2, 3, 4, 5, 6, 45 million. Over X. Okay. Now, if we want to minimize, what are we gonna do? We are gonna take the derivative and then set it equal to 0 to find the critical point. So this will be 5. This is also, you can rewrite it as 45 million x to the negative 1. So I have negative 45 million x to the negative 2. Let's set that equal to 0 to find the critical value. So adding 45 million to the both side, x to the negative 2. I'm going to have 5 is equal to 45 million over x squared. Create proportion, so 5x squared is equal to 45 million divided by 5. X squared is equal to 9 million. Let's square root. So I have x is equal to plus or minus 3,000. Because x represents number of boxes, it doesn't make sense to have a negative number of boxes. X is equal to 3,000. Okay. So now let's check. So x equal 3,000 was our critical value. Now to minimize, what we are going to do is we are going to take the second derivative. So we got the first part checked. That's where the x is, when you take the derivative and then set it equal to 0, we got that c, or in this case x, is equal to 0. We need to check this one. So let's take the second derivative. Our first derivative was right over here. Our first derivative function is this one here. So let me put it here. C prime of x was 5 minus 45 million x to the negative 2. And then our double prime will be 5. And then this one with this one makes it positive 90 million x to the negative 3. Okay. Let's plug it in 3,000 onto our function, because that's our x value for the critical value, and see if it's a positive number. Okay. I end up getting with the calculator. Let me just double check. So we get 5 plus 90 million. Oops, to the negative 3. I got 5.003, so about 5. So that is a positive number, so check. So that means since C double prime at 3,000 is positive, greater than 0, the minimum cost occurs when x equals 3,000. So what does it mean? We want to know how many to produce the number of boxes. We are actually looking for how many the production runs. So this is when we set up the cost function, this was our production run function. So let's find out. So this was our production run function. So don't forget, when we set up the cost, we did this many boxes divided by x. So finally, we are going to have 180,000 divided by x, which is 3,000. We get 60. So our final answer will be the company should produce boxes of bandages. $60 times a year. Okay. That's it. That's all the section for 4.6. And that's the end of chapter 4.